candidate, Michael Dairyko, who's going to be talking to us today about exponential domination on graphs.
Thank you so much for everyone coming here. It means a lot to me, and I'm going to tell you about a story about exponential domination. So I have an outline, so we're going to start off with preliminaries. So I'm going to get into the basic the notations and definitions. I'm going to get into some background of the problem. I'm going to get into what exponential domination is. So overall, big picture, what is exponential domination? It is contained in something called Domination Theory. So domination in graphs. It's a tool used to analyze situations in which an object exerts influence on the surrounding objects. So in terms of a vertex, we have a vertex that exerts influence on its surrounding vertices. All right, so I'm going to give you some definitions now. First of all, we're going to start off with a graph, which is a collection of edges and vertices. And I'm going to have a set of vertices D. So my first definition is a weight function. You input two vertices, vertex U and vertex V, and we say that vertex U assigns weight W to vertex V. So whatever vertex is in the first component is the vertex that's sending the weight, and whatever vertex is in the second component is the vertex that receives the weight. Okay? So a vertex can send a weight to itself too. So I have a set or a vertex sending weight to a vertex. We can have a set of vertices sending weight to a particular vertex, and a particular vertex sending weight to a set of vertices. So I wanted to give a quick example of what a weight function is. So here this weight function is the weight that D sends to V is going to be 1/2 if the two vertices are adjacent or if they're distance 1, and it's going to be 0 otherwise. So I have this graph on 6 vertices, and my vertex D is filled in blue. We're going to see what the weight that vertex D sends out to the graph. Right? So these two white vertices are adjacent, and it's adjacent to itself, right? So those 3 vertices all receive weight 1/2, and everything else receives weight 0. All right, the next definition I'm going to talk about is what domination means, or to dominate. So we have a pair, dW, where D is a set of vertices, and W is a weight function. We say this dominates the graph G if the weight that D sends to V is at least 1 for every vertex. So no matter what variant of domination we're working with, this is the main condition, right? You're given a weight function, you want to find a set of vertices D, such that when you pass D through, or you send out all the weight from D to a vertex, you get at least 1. Okay? So the original dominating problem, or classical domination, is as follows. You have a set of vertices. It's considered to be a dominating set if every vertex that's not in that set is adjacent to at least 1 vertex in that set. Okay? Another way of defining it is in terms of its weight function. So here, the weight that D sends to V will be 1 if they're adjacent and 0 otherwise. So I have another example. I have this graph on 10 vertices. I have 3 blue vertices and 7 white vertices. I'm going to show to you guys that the 3 blue vertices form a domination set. Right? So look right here, right? These 2 vertices are all adjacent to this 1 blue vertex. These 3 vertices are adjacent to this blue vertex. And these 2 white vertices are adjacent to this blue vertex. Right? So if I pass these through the weight function, I show that the weight that the 3 blue vertices send each of the individual white vertex is exactly 1. Right? So the condition is satisfied. So the 3 blue vertices form a dominating set. Right? And notice that this is also a minimum because I can't do this with 2. 3 is the smallest number that I can do this with. All right, so now I'm going to get into the background of the problem. All right, so I have a chessboard on the screen. Right, for those of you who don't know anything about chess, it's a 2-player game of strategy. You have 16 pieces to start off with. You have 8 pawns. You have 2 bishops, 2 rooks, 2 knights, and a king and a queen. Okay. So the queen is the most powerful chess piece, right? Because it can move any number without any obstructions. It can move any number of tiles in the horizontal, vertical, and diagonal directions. So here's an example of all the potential moves of the queen. So the reason why I bring this up is because in the 1850s, chess enthusiasts studied problems relating to sets of chess pieces that could cover a chessboard, right? So in particular, the one that I really liked was something called the 5 queens problem. So you have an 8x8 chessboard, right? And you want to know the smallest number of queen chess pieces that I can put on the board, such that all the white tiles are covered. What I mean by covered is that every white tile can be reached by at least 1 queen in 1 legal move. Right? So for instance, right here, right, this can be reached by this queen piece and that queen piece. Okay? So 5 is the smallest number where this is possible. There's a while there where they thought it was 6, but Later they were able to show that it was 5. Fast forward 100 years later, in the 1950s and the 1900s overall, more of these problems started arising, and they started relating them to graphs and their variants of dominations offshoots that started happening. So this field kind of blew up in like the 1950s. So exponential domination. All right, overview. It was first introduced in 2009 by Dinkelman et al. And essentially, they wanted to model a situation in which the vertex exerted weight in the following way. As the distance increased, the influence or the weight that it sent out decayed exponentially. Okay? So there was no such framework at this point, so they decided to create this new framework for this particular type of distance domination. All right? So you're probably wondering, what's the real-world application of this, right? So what this studies, or what this models, is the dissemination of information in a social network. So for example, I have a source, right? If I directly get my information from a source in a social network, it's completely reliable, right? And the game is if you are, as with every share of this information, right, the reliability decreases by a factor of 1/2. Okay? So I want to find the smallest number of sources to have in my social network, such that everyone involved in the social network can get 100% reliable information. Okay? So that's what we're modeling. So there's two parameters in exponential domination. There's something called porous and non-porous exponential domination. So for the rest of this section, or in the preliminaries, I'm going to talk about what it means to be porous and non-porous. All right, so in porous exponential domination, there's a weight function, W star. Now the weight that descends to V with respect to W star is going to be 1/2 to the distance between those two vertices minus 1. And when I mean distance, I mean the length of the shortest path from those two vertices. Okay, so a set of vertices D is considered to be a porous exponential domination set if the weight, or if the set D along with the weight function W star dominates the graph. Okay. Then we're interested in minimization here, so we want to find the smallest porous exponential domination set. So the porous exponential domination number is just the size of the smallest porous exponential domination set. All right, I wanted to do a quick example of this so everyone could get a feel for what was going on. So I have my graph, and I have these 4 blue vertices, A, B, C, D. I'm going to show to you guys that these 4 blue vertices form an porous exponential domination set. All right, so let's zoom in over here to vertex K, and I'll explain why vertex K receives weight 1. Okay, so B sends weight 1/1/2 to vertex K. A sends weight 1/1/2, 1/4. And C and D are both equal distance. They send weight 1/1/2, 1/4, and 1/8. So an 1/8 plus an 1/8 plus a 1/4 plus a 1/2 comes out to be 1. So we see that these 4 vertices send sufficient weight to this vertex. If I mimic that argument for everything on the bottom row, I'll get exactly 1 for each one of these vertices. And similarly, everyone for this row will get 2. So the weight, those 4 blue vertices sent to the remaining vertices that are white, everything gets at least 1. So this forms a porous exponential domination set. It's also.
You compute the 2's.
How do I compute the 2's? So this sends weight 1. This sends 1/1/2, and they both send 1/1/2, 1/4. Yep. So it all is sufficient. And I can't do this in 3, so the porous exponential domination number here is going to be 4. All right, moving on to non-porous exponential domination. It's defined very similarly, or at least the 2 weight functions are, with the exception of this distance bar. Okay, so what I mean by this distance bar is the length of the smallest path from vertex D to vertex V, just that there's no internal vertices contained in D. Okay. So that set of vertices D is considered to be a non-porous exponential domination set if D with W sub E, who back here together, dominates G. The non-porous exponential domination number, similarly as before, is just the cardinality of the smallest non-porous exponential domination set. Right? So I have the same graph.
I have a question just about the distance. What happens if there are no paths between your 2 vertices that don't go through D?
So then it won't send any weight, and it won't be a dominant
So it'll just
set.
be 0?
Yeah.
Okay.
Yep. All right, so here's an example. It's the same graph, but instead of having the top 4 vertices, A, B, C, D, being the dominating vertices that we're going to consider, I'm going to show to you that the non-porous exponential domination set is actually going to be E vertex E through vertex J. Okay, so we're going to zoom in on vertex K again, and this time it's going to receive exactly weight 1, because the distance from E to K is 1, so it gets weight 1, right? But notice, from K to any of these other 5 vertices, blue vertices, right, there's an internal blue vertex. So that means that this internal blue vertex blocks the weight that these 5 vertices send out. So this can't get anything from these 5 vertices. So a similar argument has everything on this bottom row getting exactly the weight 1. Right, and then up here, right, if we zoom in on this vertex right here, there are no paths to any of these blue vertices that contain an internal blue vertex. So that means it can receive weight from all 6 of these vertices, right? So if you sum up the weight that all 6 of those vertices send, it's going to be 3 for the remaining 4 blue or white vertices. Okay? And again, you can't do this in 5 vertices, so 6 is going to be the non-porous exponential domination number. All right, and some quick observations. All right, so with domination overall, right, it was worried about, the influence was with things within distance 1, right? So that's a very local influence. Other forms of domination also have a local influence where the distance can be some radius of k that it can exert influence on, right? Exponential domination differs from all these other variants because it's a global influence. So one vertex can send weight out to all the other vertices in the graph, right? So this is the only such variant of domination that has this property. So it makes it kind of hard to study, and it's one of the reasons it's been cited as being possibly one of the reasons why there's not a whole lot of literature and a lot of research being done here, because it's kind of hard to bound the weight that can get sent out. Another observation is that the non-porous, or the porous exponential domination number is less than or equal to the porous or non-porous exponential domination number, right? So with our graph that we had, this value was 4 and this value was 6. It kind of makes sense why that happens, because there's blockage that occurs with non-porous exponential domination, so you need more vertices to cover everything, right? In porous exponential domination, the word porous means seeping through, right? So the influence seeps through, so you need less vertices to get the same amount of coverage. The last thing I want to talk about is something called subcubic graphs. This has maximum degree at most 3. So the degree is, if you have a vertex, there can be at most 3 edges protruding from the vertex, right? A lot of the literature focuses on subcubic graphs because subcubic graphs align with exponential domination. There's a way to somewhat localize the influence that gets sent out, right? So that's a reason why a lot of the people in the literature use subcubic graphs. What I work on, the graphs I've worked on aren't subcubic, right? So that was carving out just a little hole in the exponential domination area that no one really has worked on too much. So that's all for the observations. So we move on to the generalized circulant graph. Okay? So I'm going to talk about some notation definitions to get you up to speed, and then I'm going to talk about a uniqueness result I have, and then get into my main result. Yeah?
Has anyone considered like 1 over k instead of 1 over 2 for the exponential domination?
No, they have not.
Okay.
No. So the growth factor being 1 over 2 has been pretty standard throughout the literature. All right, so you're probably wondering what a generalized circulant graph is. Okay, we denote it as C sub n L. That bracket L just means the set of integers from 1 to L. It's a set of n vertices such that vertex V is adjacent to vertex V plus or minus I for every I in L. Okay, so I have an example, right? I have n being equal to 8 and L being equal to 1. So I have 8 vertices that are labeled 0 through 7, and there's adjacencies for vertex 1 plus or minus 1, right? So vertex 1 is adjacent to vertex 0, and it's adjacent to vertex 2. Now the graph C82, right, underlying has C81, but there's the additional blue edges that I put in for adjacencies plus or minus 2. And similarly for C83, C82 is in the underlying graph, and there's the additional edges in red for plus or minus 3. Okay. So, notation. So this following notation is going to help us with the next result I'm going to talk about. I'm going to assume that 3L plus 1 divides n, right? This L comes from the circulant graph. And I'm going to have a set of vertices, D, okay? Now I'm going to label the vertex set of my circulant graph is going from 0 to n minus 1, but I'm going to rewrite n as 3l plus 1 times m, just to help with some of the notation later. So I is going to be a partition of the vertices, this consecutive partition, right? And we partition the vertices into m parts, or m intervals. Each interval has length 3l plus 1. Okay, that's all that means. Then I have these three functions, right? So the first function, f sub k, it's related to d. It's also related to I, and it represents how many vertices of d are contained in the kth interval. Okay. Z of d comma I is just going to tell me how many intervals contain no members of d. And lastly, f star of d comma I is going to be the maximum number of elements contained in d that can be in any given interval. Okay. So if that was confusing, I have an example just to help you guys understand my notation. So in this case, I have C14, 2, so that means n is 14, so I have 14 vertices. I'm labeling it 0 through 13. My L is 2, so I have adjacencies plus or minus 1 and plus or minus 2. And my D here is going to be the set 1, 3, 5, 7, 9. Okay? So by my partition, right, L is equal to 2, so 3L plus 1 is 7. So I'm partitioning it into two parts in each of length 7. Okay? So this is interval I0, right? So it's 0 through 6. It contains 3 vertices of D, 3 members of D. So that's why f sub 0 is equal to 3. Similarly, in I sub 1, right, there's 2 members of D, so f sub 1 is going to be equal to 2. Now there are no vertices, or there are no intervals that contain no members of D, so z is equal to 0. And lastly, f star is going to be equal to 3, because the most number of members, or the largest number of elements contained in D are going to be, in a given interval, is 3. Okay. All right, so we get to our first theorem. This says that if n is equal to 3l plus 1, and D is a minimum porous exponential domination set, and we're going to consider the partitioning I that we just discussed, then f star is going to be equal to 1, and z is going to be equal to 0. And furthermore, D is unique up to isomorphism. Okay? So z being equal to 0 means that when I partition my interval into m parts, right, every part has to have at least one member of D. And f star being 1 is actually saying there's exactly 1 in each interval, right? So if I count that up, I have m partitions. Each partition has exactly 1 member of D, right? That means D has m members, right? So a direct corollary from this theorem is that if D is a minimum porous exponential domination set, then the size of the smallest, or the minimum exponential, or porous exponential domination set is going to be m, okay? So this is a really strong result because it gives me an exact value, but it's with the condition that 3l plus 1 divides n. Okay? So what I'm going to do now is go into the overview of the proof for this theorem, and then we're going to get into our main result. All right. So big picture, what did I do for this theorem? To show that f star is 1 and z is equal to 0, I use something called double induction. Specifically, I have f star and z. If I bound that sum up above by 3l plus 1, and I sum the bound below by 2, I show that D cannot be a minimum porous exponential domination set. Okay? So then if I take the contrapositive of that statement, I say D's minimum implies f star plus z is equal to 1. Okay? And then for the uniqueness, I just have the counting argument, and I'll do a proof by picture on that one. And that will result in the theorem being proved. So for the induction, double induction, with double induction, there's going to be 2 base cases. I like to think of it as like a chart, right? So you fix one of the parameters, right, and you iterate through the rest of them. So that's going to be base case 1. And base case 2 is fixing the other parameter and iterating through the other one, right? So that will be base case 2. Okay, so before I get started, I was able to come up with a porous exponential domination set that has size m. Okay? So that means that the minimum size, or so the porous exponential domination number is bounded above by m. Right? If you have the construction of something, you can only improve it, you can't worsen it. Okay? So in the case where f star is greater than or equal to 2 and z is equal to 0, right, that means that there's m parts, no parts are empty, and there's at least one part with 2 vertices. Right? So if you add that up, that gives you at least m plus 1. Right? my size of D is at least m plus 1, it can't be minimum because on the side I already have something that's better. Okay? So in this case, I've shown that D cannot be minimum. In the case where f star is equal to 1 and z is greater than or equal to 1, right, that means I have at least one interval that contains no dominating vertices. Okay? So what I do here is I choose one of those vertices, I maximize the weight that D can send to that particular vertex, right, and I show that that doesn't receive sufficient weight. So with the maximization, right, if that doesn't receive sufficient weight, then with my original set D, it can't give sufficient weight. So that means that in this case, D couldn't even be a porous exponential domination set to begin with. Okay? So I showed that D was not minimum for base case 1 and base case 2. And for the induction step, right, I'm going to show the same thing. I'm either going to show that D is not minimum, or it couldn't even be a porous exponential domination set to begin with. All right, so in induction hypothesis, I assume that this condition holds the sum for the sum being strictly less than alpha. And then for my induction step, I'm going to assume that this sum is equal to alpha. Okay. Now I have three subcases. I have f star being bounded below by 4 and bounded above by 3l plus 1. I have f star being equal to 3 and then f star being equal to 2. All right. So in the first case, right, remember before I said that I have a set that has size m, right? So counting-wise, if f star is at least 4, then that means that z has to be greater than or equal to 3, or else I'll have a set that has size more than m. So that's why I have z being greater than or equal to 3. So here I have a shift algorithm, right? So I have my dominating vertices in the circulant graph. I have an algorithm that shifts these vertices, the dominating vertices, just a touch, so that all the vertices in the graph get a little bit more weight. There's not one vertex that doesn't get the same amount of weight. So it only improves the weight overall that the graph, or the vertices in the graph get. And when I do this shift, I can show that f star of d prime plus z of d prime is bounded above by alpha minus 2 and below by 3. Okay? So I can apply my induction hypothesis here, and because this is strictly less than alpha, I know that this implies that d prime cannot be a minimum exponential domination set. Okay? So in the second case, right, there's going to be two subcases. But starting off, f star is going to be equal to 3 for the same reason as above. Z has to be greater than or equal to 2, or else I'll have my d being too big. Okay? I'm going to use the same shift algorithm and construct a new set d prime with the fact that z of d prime is greater than or equal to 0, and f star of d prime is bounded below by 1 and bounded above by 3. So when this happens, I have two cases, right? My f star of d prime can be greater than or equal to 1, and my z of d prime can be greater than or equal to 1, or my f star of d prime can be 1, and my z of d prime can be 0. Okay? So in this case, the same thing as I've done before in the previous case, right? This d prime, by the induction hypothesis, can be a minimum porous exponential domination set. All right? So moving on to the second case, when f star is 1 and z is equal to 0, that gives me a lot of information about the original structure of D. Okay? So I use that knowledge to find a vertex that doesn't receive sufficient weight in this case. Okay? So in this case, I show that D cannot be a porous exponential domination set to begin with. Okay? So similarly, like with the base cases, I either showed that it was not minimum or it couldn't be a porous exponential domination set. Lastly, for f star being equal to 2, same as before, my z has to be greater than or equal to 1, and I have two cases. My first case is when z is greater than or equal to 2. My second case is when z is equal to 1. Okay? Again, when z is greater than or equal to 2, right, I can shift the vertices in a way such that I come up with a new set d prime that gives me, that's bounded between 2 and alpha minus 1, and I can apply my induction hypothesis. So this cannot be minimum. D prime can't be minimum means D can't be minimum. And then lastly, when z is equal to 1, right, this gives me a lot of information about my original set D, right? So I go back there, I can find a vertex that doesn't receive sufficient weight, and it can't be a porous exponential domination set to begin with. All right? So at this point, we're done. We've gone through all those cases, and the result holds by induction. Okay. All right. Next claim for its being unique up to isomorphism. It's a lot nicer of a proof because it's going to be a proof by picture. All right, so what I'm doing here is I'm going to suppose that vertex 0 is contained in D. okay? I know f star is 1 and z is 0, all right? So I'm going to choose my partition such that vertex 0 is contained in I0, and I'm going to have the partition, so the length of each interval is 3L plus 1, and there's going to be m parts in the partition, okay? So since f star is 1 and z is 0, I know that since I chose 0 to be in D, any vertex 1 through vertex 3L can't be a member of D, okay? So now I'm going to do something sneaky and shift my partition over by 1. So now vertex 0 is contained in IM minus 1, all right? We still know that vertex 1 through vertex 3L, that can't be a member of D. So the only, and f star is 1, so the only potential, or the only possible way to have f star be 1 here with this shift is if 3L plus 1 was contained in D, okay? So if I keep on iteratively doing that argument over and over again, I can build my set D, and it's going to be 3L plus 1 times K, where K goes from 0 to m minus 1, right? So it's now unique up to isomorphism because depending on where you start, right, you can build a similar set D, but they're pretty much all the same, so that's why we say up to isomorphism. And that's the end of that proof, okay? So that was the end of that previous theorem, right, and I was able to come to the main result. I'm really excited about this because I was actually able to come up with an exact number for the porous exponential domination number of the circulant graph and the non-porous exponential domination number of the circulant graph. Normally in domination, you can only find upper bounds and lower bounds. Being able to actually find an exact number is tough, so I was really excited when we were able to come up with this result. So I'm assuming in this case that n is equal to 3L plus 1, m plus r. So essentially, right, n can be any number bigger than or equal to 4, right? So that's why this is general. Then we have that the porous and non-porous exponential domination number of this particular graph is going to be equal to the ceiling of n over 3L plus 1. Okay. So I'm going to go over the proof, big picture, right? First of all, there's two cases. I'm going to assume r is 0 or r being greater than 0. When r is equal to 0, it's a little bit of an easier proof, and I'm going to talk about r being greater than 0 because more of the fun stuff kind of pops out. So there's three subcases. I'm going to show a lower bound for the porous exponential domination number, right? Earlier in my observations, we discussed why this bound holds, right? Because of blockage with the influence. And then lastly, I'm going to show there exists a construction for a non-porous exponential domination number that has size n over 3L plus 1, right? So I have this series of inequalities. And the only way for these inequalities to all hold is if there's actually equalities, okay? So first claim, I'm going to show the lower bound, and we're going to be working with porous exponential domination. So I'm going to assume that I have a minimum porous exponential domination set D that has size at most m, okay? So when I do this, I'm going to choose my partition such that I have I'm going to partition the vertices into m plus 1 parts, right? M of them are going to have length 3L plus 1, and one's going to have length r, okay? Now because I'm assuming that D is greater than or equal to m, and I have m plus 1 parts, right? One of the parts can't contain a member of D. So I'm also going to choose my partition so that there can be no members of D in IM, okay? I'm going to let n prime be equal to 3L plus 1 times m, and I have a mapping phi that goes from the vertices of Cn to the vertices of Cn prime, where any vertex contained in IM just doesn't go in. Okay? Now the reason why I dropped down to here is my previous theorem. We know that f star is going to be 1 and z is 0, and that the exponential domination set, the minimum exponential domination set down here is going to be unique up to isomorphism, right? So up here, remember, D has size at most m, right? D is not contained in IM, so the members of D up here get dropped down to a new set down here, right? And because it worked up here, there's less vertices down here, everything's closer, that same set has to work down here, all right? Because this has size m down here, right, by that previous theorem, we know f star is 1, z is 0, and is unique up to isomorphism, okay? So here is where I'm going to put all my vertices that are in D, right, and they're all 3L plus 1 apart, okay? So vertex 0, vertex 3L plus 1 is all in D, all right? So now I'm going to map back and look into my original circulant graph, right? And because I know where the vertices are here, I know where they are in this graph. Okay? So now I'm going to do a sneaky thing by shifting my partition over by R. When I shift my partition over by R, vertex 0, which used to be in I0, is now contained in IM minus 1. Okay? Now my new partition, right, I have vertex 1 through vertex R being in IM. None of those vertices are contained in B. Okay? And my 3L plus 1, which is right here, is now in I0. So I'm going to shift back into Cn prime one last time, right? So these R vertices here get mapped to nothing. They're N prime vertices right here, right? Now the distance up here between every blue vertex is 3L plus 1, but the distance right here between these two blue vertices is 3L plus 1 minus R, okay? Now that's a problem. Now D, remember, is 3L plus 1 times I, right? D fails uniqueness up to isomorphism because that last time I mapped it back, the two vertices weren't distance 3L plus 1, they were less than that, okay? So in the size of D in this case is n. So I've shown that there can't be a porous exponential domination set or minimum porous exponential domination set of size n or less, okay? So that means that the size has to be m plus 1, or it potentially could be m plus 1. So m plus 1 is actually equal to the n over 3L plus 1, right? So this is going to be the new lower bound for the non-porous, or the porous exponential domination. Okay? So through that argument, I was able to show step 2. My next slide, I'm going to start on step 3. And this one is, again, a proof by picture, so you'll probably like this a little bit better. So remember, my n is equal to 3L plus 1m plus r. Okay? My vertices are going to go from 0 to n minus 1, but I'm going to rewrite my n in terms of 3L plus 1m plus r. My goal here is to show, so this is the circulant graph, and I have vertices 0, or vertex 0 through vertex 3L plus 1 shown, right? And I got rid of the edges. I'll add those in a little bit. I'm going to show that vertex 0 and vertex 3L plus 1 dominate vertex 1 through vertex 3L with non-porous exponential domination. All right, so let's look at vertex 0. Right, so the adjacencies, remember in CNL, there's adjacencies plus or minus 1, plus or minus 2, all the way to plus or minus L. So that means 0 is actually adjacent to vertex 1, all the way up to vertex L. Okay, so the weight with respect to non-porous exponential domination that vertex 0 sends to this group of vertices is going to be exactly 1. All right. Similarly, on this side, this red vertex, 3L plus 1, will send weight to these L vertices, and this is distance 1, so it receives weight 1. Right? Everything in the middle is distance 2 from vertex 3L plus 1 and vertex 0, so everything in the middle gets exactly weight 1/2. Okay? There's more weight that gets distributed, but we can stop here, because I've shown every vertex between vertex 1 and vertex 3L, including 1 and 3L, receives at least weight 1. So with respect to non-porous exponential domination, right, everything in the set 0 to 3L plus 1 receives sufficient weight. Okay? So remember, we're trying to show this upper bound, so that means we have to show a construction. So I have to show that there exists a non-porous exponential domination set that has this cardinality. All right, so if I apply that argument, right, and I place my dominating vertices at most 3L plus 1 apart from each other, right, I can construct a set of vertices that I call D prime, such that so from here to here, all these vertices get dominated, all of these vertices get dominated, all of these vertices get dominated, and so on. So I was able to construct a non-porous exponential domination set that has size m plus 1. Okay? So that gives me an upper bound. And the theorem is proved at this point. Okay? So that was it. That result was really exciting for me because, again, you get to have an exact number instead of bounds. So for the last part of my talk, I'm going to go over my concluding remarks. So I'm going to get into some of the other results that I've had that were also important to me. And I'm going to talk about things, ideas for the future, for things that people can work on. All right, so for my preliminary exam, a lot of you weren't there, so you might not remember, so I'm going to go over some important definitions. I have something called excess weight. So the condition that is important with domination overall is that everything gets weighted at least 1. Anything over 1 is considered excess. Okay? Total excess just sums up all the excess in the graph. And then I have something called maximum weight, M of G. This function just computes the maximum weight a particular dominating vertex can send to the vertex set. Okay? So we came up with this theorem for a lower bound. We say let D be a porous exponential domination set such that K times the size of D is less than or equal to the excess of D. Then we can lower bound the size of D by the size of the vertex set over the maximum weight sent out minus K. Okay? So you're probably wondering, why do I have this condition here? This condition ensures that I don't scrape off enough weight or too much weight in the bottom and have a vertex that doesn't get enough weight. So the really cool thing about this theorem is that this holds for all graphs. This is a very general theorem for porous exponential domination, and it only has 3 parameters. The size of the vertex set, right, most of it should be known, so that's an easy thing to find. M of G isn't too difficult to find. The only hard thing to do is to find a value of K. But worst case, naively, we could say K is equal to 0. So with this theorem, we'll always be able to find a lower bound. Okay? So I use that theorem to find the lower bound in the next 3 graphs that I'm going to talk about. So the first graph is the n-dimensional hypercube. So the n-dimensional hypercube, its vertices can be encoded in binary, and their two vertices are adjacent if in their binary representation they only differ by 1 bit. Okay. Another cool property of the hypercube is that so this is a 4 cube, right? A 4-dimensional hypercube, and in the 4-dimensional hypercube, you can see that there are 2 cubes. There's a red cube and a blue cube, right? And there's a perfect matching between those 2 cubes. What I mean by that is the leftmost vertex here in the red cube is adjacent to the leftmost vertex in the blue cube, right? And that follows all the way through. Okay, so that's what an n-dimensional hypercube looks like. And then the theorem that we came up with, that we're able to bound the porous exponential domination number of this n-dimensional hypercube above by the square root of n, or the square root to the nth power, and below by this value, right? And this is an application of that theorem that I previously talked about. We had to find what the size of the vertex set was, which is 2 to the n. We had to find what m, the maximum weight a particular vertex could send out. We had to find a value of k. Okay. So I'm going to show this lower bound because I really like the construction, and how we went by, or not the construction, but I really like the proof point. So for the lower bound proof sketch, we're going to have D being a minimum porous exponential domination set, and I'm going to assume that D is a member of D. So little d is a member of big D. Okay? So the first thing we're going to do is find Q of M. Right? So here, the weight that D gets sent out to the vertex set, we can realize that as this sum, right? So remember how I said that we can encode the vertices in binary representation, right? So n choose I counts the number of vertices that are distance I from D, okay? And that happens because your distance I, you have to switch, you have to perturb I bits, all right? The weight that something will send, so 1/2 to the I minus 1 is just the weight that vertex D will send to something that's distance I away, right? So summing through all of this will compute all the weight that D sends to the vertices, all right? With some doing a couple algebraic manipulations to the summation, we can apply the binomial theorem, right? Which gives us that this value, or this summation, is going to be equal to 2 times 3/2 the n, right? So because this same summation holds for all D, right? We can have m of q of m, the maximum weight that a particular vertex can send out is going to be 3/2 to the n times 2. Okay, so that's our value of m of q n. Now the last thing we have to show is how to find a value of k. Okay, so I'm going to assume that D, my dominating exponential domination vertex, is going to be as a binary representation of all zeros. Okay, now A is going to be the set of vertices in Qn whose binary representation has an odd number of ones, and B is going to be the set of vertices in Qn who have an even number of ones. Okay, so there's going to be an edge from D to something in X, right? X is going to be the set of vertices that have exactly 1 1 in their binary representation, Y is the set of vertices that have exactly 2 ones in their binary representation. Okay? So, right, the D is a binary word of length m, right? So X is going to have exactly n vertices, right? Because there's n ways to switch 0 into 1, right? So these are, everything here is distance 1, and everything in here is going to be distance 2. Okay? So if I count the weight that this particular vertex sends out to the set X, right? It's going to send weight 1 to each vertex in X, and there's n vertices in X. Right? So the weight that D sends to X is going to be n. Alright? So it's going to send weight 1 here and send weight 1/2 here. Right? So there are n vertices in vertex Y, or in the set Y, so it's going to send weight n over 2 to the vertices of Y. Then lastly, D is going to send weight 2 to itself, because 1/2 to the 0 minus 1 is going to be 2. Right? So that's the weight that this particular vertex in D sends out. If I consider all the other vertices in D, right, to ensure, because we're assuming that it's a porous exponential domination set, it has to send at least weight 1 everywhere, right? So that means everything in here has to get at least weight 1/2 from the set D without D, right? So everything in here has to get total at least n over 2, right? So that means everything here has to get n over 4, and that this particular vertex has to get 1/8 from the dominating vertices without D. Okay? So let's count the excess weight. Right? Every vertex has to get at least weight 1. We've shown that everything here does get at least weight 1. But every vertex in this set gets an extra 1/4. Okay? So if I count that up, that means that there's an excess weight that D sends to the set X. It's going to be at least n over 4. All right? So D gives weight 2 to itself, and it receives at least weight 1/8 from all the other vertices, right? So 2 1/8 minus 1 is 9/8, right? So if I add up this excess weight, right, I get a lower bound of 2n plus 9 over 8 times, and this is per value of D, right? The size of D is how many members of D there are, so the total excess is bounded below by 2n plus 8, or 2n plus 9 over 8 times the size of D. Now, this is going to be my value of k, right? So if I use that value of k, the value of m of qn that I found, and I know the size of the vertex set, I can apply that to my theorem, and that's how I got the lower bound. Alrighty, the next graph I want to talk about is the King grid. I really liked working with this graph because it brought us back to the chessboard representation that I talked about earlier. So, if you encode the tiles in a chessboard as vertices, right? And you have a king chess piece, there's going to be the edge between those two vertices if you can make a legal move with your king chess piece. Right? So for instance, if the king chess piece was right here, right, there's 8 potential moves that it can make, so there's 8 vertices. Alright? So I was able to show that for all n greater than or equal to 23, the porous exponential domination number of the King grid has a lower bound of n squared over 23.3 and has an upper bound of n squared over 23. Right, so these bounds are really, really close. And for the lower bound, right, n squared is how many vertices there are. I was able to find the value of the maximum weight, so my m of qn. That ended up being 34. And how I found my value of k was through using something called linear programming. Right? So linear programming takes in a bunch of linear constraints subject to a linear objective function, right? And it gives you the optimal solution. So in my preliminary exam, I kind of discussed more about the linear programming, so I'm not going to get too much into that, but I use this technique to find my value of k. Okay? And then lastly, I worked with something that I called the slant grid, right? Which essentially is the King grid, but with one directions of diagonals taken out. Okay? So similarly, for all n greater than or equal to 19, my lower bound for the porous exponential domination number is n squared over 19.7. My upper bound is going to be n squared over 19. And similarly, n squared is the number of vertices. I think for this one, the maximum weight of particular vertex to send out was 26. And I used a similar linear program to figure out my value of k. And also one thing that I forgot here is that I conjecture that this lower bound actually is going to be n squared over 23. And then for this one, I have the conjecture that this lower bound is actually going to be n squared over 19. Okay? And then next steps, so things that I think would be fun to work on in the future, would be for someone to explore exponential domination in terms of a growth factor key that's between 0 and 1. So basically what Alex's question was, if someone worked on it or we've only worked on it in terms of 1/2, maybe using 1/3 or 1/5, right, to see if we get similar results. Also, to add constraints to my linear program that I constructed. So for that lower bound, I did some work on it. I wasn't able to really come up with anything of substance, but to find an additional constraint to add to help increase that lower bound, so that 1/23.3 and that 1/19.7, just to increase it a little bit to get the 1/19 or 1/23. Another thing I think would be interesting would be to study exponential domination on strongly regular graphs because they have nice distance properties, or to look into other types of circulants. So the generalized circulant graph, right, the non-porous and porous exponential domination number were equal. I want to know, is that true for all types of circulants, or is there some property just with the generalized circulant graph that makes that happen? And then I want to give a quick shout out to my advisors, Michael and Leslie. Thank you so much for these couple of years doing research. I really appreciate it. The other people on my committee, James, Bernard, and Steve, thank you guys so much. You guys have all taught me really well. Everyone who came, my friends, thanks so much. Thanks.